All right, rolling the sleeves up for this one. Okay. No, it's probably not that bad. It's probably not that bad. But we're talking about torque. And torque can be a little hard. Let's work on this problem. I have a rod of like 18 meters. All right, let's note that. 18 meters is this whole thing right there. By the way, this should look really, really familiar. I think the last one on the activity, if you're able to complete that one, right? If not, well, here we are. Let's do this. So it's 18 meters long. There's axis of rotation at the center. So this is my axis of rotation, that big black dot right there. F2 and F3 are located midway between the middle of the rod and the end. Okay, I'm going to calculate the torque if I'm given F1, F2, F3, and theta. Okay, so first things first, let's calculate a net torque. My net torque, and that's equal to I times alpha, right? But this is going to equal to, well, let's say I have torque due to 1 plus torque due to 2 plus torque due to 3, right? So if I'm looking at this, it's going to look a little bit, this is going to look a little bit different than the table method, but you know, it's okay. We just have to remember for each torque, I have to calculate magnitude of F, magnitude of R times sine of theta. And I have to remember that a counterclockwise torque is positive and a clockwise torque is negative, right? So let's start making my substitutions here. Let's see, start with F1. So F1, this guy right there, I'll call this R1. There's R1, F1, and it looks like I have an angle between the two. That's going to be about 90 degrees. Okay, so my net torque is going to equal to F1, R1, times sine of 90. Now let's say positive or negative. Let's see, here's this. I have a force here going this way. I see something that is going clockwise. To me, that's going to be a negative. Well, not just to me, it's going to be a negative. It's going to be a negative. Why? Because it's making this thing go clockwise. All right, next, let's do number 2. So there's R2 right there. Remember, this R value is the radial distance. It is the straight line distance. Whatever, you start at the axis of rotation and then you draw a line to where that is being applied. That force is being applied. And there's F2 being applied right there. Okay, so let's see this guy here. What's this going to do? It has a downward component. Only the downward component is going to make this thing rotate. So I'm going to see something that's going counterclockwise. This is going to be positive. So I have a plus magnitude. So this is plus F2 times R2 times sine. Okay, so the angle in between, technically, oops, not you. I want that angle right there. That angle between is that angle theta. So I want sine of 21, right? I'll just put theta for now, right? Because everyone will have a different one. The 90s will be the same for everybody. The other one will not. If you ended up using 180 minus that theta, that's completely fine. Because you'll find out that the sine of 45 is the same as the sine of 135, right? So technical point, but calculation-wise, it'll end up being the same. All right, last one is F3. F3. Okay, so here's F3. F3 is pushing down this way, right? And it's going to make this thing go clockwise. Yeah, that's clockwise. Clockwise is a negative. So negative F3. Oh, I didn't do my R. Where's R3? There you are. R3, right there. F3, R3, sine of, this is also going to be 90. Right, there's 90 degrees. Right, I just want to do net torque. Net torque, right? So review, rehash, right? Net torque is the sum of all the torques. Just like net force is the sum of all the forces, right? I have to add up all my torques. So I assign a torque to every single one of my forces on my free body diagram. And when I do, I go through, just like, okay, torque 1. How do I calculate that? F R sine theta, right? F R sine theta, right? I have to do that for each one. There's F1 is being applied, R distance away, as an angle of 90. And you do that for every single one, right? Right? It's not necessarily hard. is tedious, right? So a lot of benefits there. Okay, sine of 90, all these sine 90s go to 1. So, you know, net torque is equal to, let's see, negative F1R1 plus F2 R2 sine theta, right? Put that theta in degrees, minus F3 R3 Y, because sine of 90 is 1, sine of 90 is 1. All right, you plug all these in to your my not so fancy calculator. Let's see, what do we get? Oh, lots of additions. I'm going to start with the F2. F2 is 28 times R2. Okay, so F2 and F3 are midway between. The whole thing is 18, so you have to break this up into little fourths, right? Well, so it's like 18 divided by 4. That's kind of annoying, right? So this R3 is equal to 18 over 4, or 9 divided by 2, which is 4.5. Okay, maybe not that bad. This is 9 meters right there, which means this is 4.5 meters. So 28 times 4.5, right? I take that times sine theta, 21 sine equals, I get 45. Okay, now let's see if I can do this. I'm going to subtract parentheses F1R1, which is 2 times 9, right? 18. So I'm going to subtract again, which is F3R3. So F3 is 15 times, so that is 4.5 again. Yeah, because R2, so I wrote 4.5 on the wrong one for F2, but they're both in the middle, so it doesn't really matter. 0.5 parentheses. I get a negative 40.3, which means, so what does a negative tells me? Negative tells me this thing, there is a net torque, right? There's a value, right? It's not at rest. These aren't in equilibrium, right? If they were, it'd be 0. But I have a value that's left over. So I have a net torque. That net torque is going in the negative direction. So this thing is going in the counterclockwise. Sorry, I had to pause there. Low battery. All right, so I put that in there. Like I said, mine was negative 40.3, right? And notice that you must put a multiplication symbol between the N and M. So Newton times meter, Newton shift 8 meter. Hopefully everything works out well. All right, that's like the worst, right? You get through this whole process, doing all these things, putting them in the calculator, and you get to the end, it's just like, oh my gosh, now I have to go back, right? Or you come see the video tutor, right? I'm just like, okay, maybe somewhere in there, I can see where things went wrong, right? Okay. Oof. Now, oh man, there's more. Okay, calculate the inertia of the rod if the magnitude angular acceleration is 3 radians per second squared, right? All right. Radians, that's your displacement, that's your position for net torque, right? So here's where we use the rest of applying Newton's second law in rotation. Net torque equals I times alpha. Solve for that I, which is net torque divided by the alpha. We just got the whole net torque. It's that negative 40.3, right? Let's see. So if I gotta be a little bit careful here. That's negative 40.3, right? And if you take that just straight up divide it by 3, I get negative 13 point stuff. Can you have a negative mass? No, you can't have a negative mass. You ain't gonna have a negative inertia either. You ain't gonna have a negative inertia, right? So this value should be positive. Why isn't it? Well, because the alpha should be negative, right? Turns out, your net torque is negative. So if you're accelerating, right, I'll just say you're speeding up. So it's in the same direction, must be. Okay. So this is going to be 13.4585461190. You don't need to put all that, right? Kilogram meter squared. And there it is. Ha ha. All right. Hopefully that feels good. Hopefully you learned something. And If you did, hey, press the like button. That's the best way to let people know. Like, hey, I learned something from this. Maybe you can too.